everybody, welcome back to our soil series. In part one, we learned that soil is much more than just dirt. It's a living ecosystem made up of minerals, organic matter, water, air, and countless living organisms working together beneath our feet. Today, we're taking the next step by looking at how soil actually functions. Why does one area stay wet after a rainstorm while another dries out in just a few hours? Why do some trees thrive while others struggle, even when they're growing only a few feet apart? And why do arborists spend so much time talking about something that most people never even see? The answer is because everything happening above ground begins below ground. Today, we're going to explore soil texture, soil structure, and the way water moves through the soil. Once you understand these concepts, you'll start looking at every landscape a little differently. Let's hand it over to Ty.
Before we can understand how soil behaves, we first have to understand what it's made of. When arborists talk about soil texture, we're talking about the proportion of sand, silt, and clay particles that make up the soil. Those particles didn't appear overnight. They formed over thousands and often millions of years as solid rocks slowly weathered through freezing and thawing, flowing water, wind erosion, chemical reactions, plant roots, and microbial activity. Although sand, silt, and clay often contain many of the same minerals, what separates them is their particle size. Sand has the largest particles. You can usually see individual grains with your eyes and feel their rough, gritty texture between your fingers. Because those particles are relatively large, they leave larger pore spaces between them. Silt particles are much smaller. Dry silt almost feels like flour or powdered sugar. Those smaller particles fit together more closely, creating smaller pores that retain water more than sand. Now, clay particles are incredibly small, so small that thousands of them could fit in the head of a pin. Their tiny size gives them an enormous amount of surface area compared to their volume. That large surface area allows clay to attract and hold water molecules, as well as many important plant nutrients. This is why texture influences nearly everything that happens below ground. It affects how quickly water enters the soil, how long moisture stays available, how much oxygen reaches the roots, how nutrients are stored, and even how easily roots can physically grow through the soil. Texture is essentially the foundation for every other soil property we'll discuss. So to understand why particle size matters, imagine filling 3 different containers. One is filled with marbles, another filled with BBs, and the last filled with flour. Even though each container is completely full, the amount of empty pore space inside each one is very different. Soils work exactly the same way. Those empty spaces between soil particles are called pore spaces. That may seem insignificant, but they're some of the most important real estate beneath the tree. Large pores, called macropores, allow water to infiltrate rapidly after rainfall and allow oxygen to move freely through the soil profile. Small pores, known as micropores, hold water against gravity so roots can continue accessing moisture long after the rain has stopped. Healthy soils contain both. If a soil has mostly large pores, water drains quickly, but the soil may dry out before roots can absorb enough moisture. If a soil has mostly tiny pores, water moves much more slowly. That can sound beneficial until those pores remain filled with water for extended periods, reducing the amount of oxygen available to those roots. Tree roots don't simply sit in the ground absorbing water like straws. They're living tissue. Just like every other living cell, they must respire. They take in oxygen and convert stored sugars into usable energy. That energy powers root growth, nutrient uptake, defense against disease, and countless other physiological processes. Without oxygen, roots begin to decline, even if they're surrounded by water. That's why an overwatered tree can sometimes show symptoms that look almost identical to drought stress. That problem isn't always a lack of water. Sometimes it's lack of oxygen. So if sand drains quickly and clay holds water for a long time, you might be wondering, which one is better? The answer is neither. In arboriculture, we aren't looking for the fastest draining soil, and we aren't looking for the soil that holds the most water. We're looking for balance. That's where loam comes in. One of the biggest misconceptions in tree care is that loam is its own type of soil. It isn't. Loam is simply a balanced mixture of sand, silt, and clay. Each particle size contributes something important. The sand provides larger pore spaces that improve drainage and allow oxygen to move through the soil. The silt helps retain moisture while still allowing water to move relatively freely. The clay contributes nutrient holding capacity and stores water that can be used between rainfall or irrigation events. Together, those particles create a soil that supports healthy root development. Now, that doesn't mean every tree requires loam. Trees naturally grow in sandy soils, clay soils, rocky soils, volcanic soils, and everything in between. The species and the environment matter. But when arborists describe an ideal growing medium, loam is often the benchmark because it provides one of the best balances between drainage, moisture retention, nutrient availability, and aeration. Another important concept is field capacity. Imagine a heavy rainstorm. Water fills nearly every pore space in the soil. Gravity immediately begins pulling that excess water downward. After a day or two, the free water has drained away, but the soil is still moist. At this point, the larger pores contain oxygen, while the smaller pores continue to hold water. That condition is called field capacity. This is often where soil is healthiest for plant growth because roots have access to both water and oxygen at the same time. As the soil continues to dry, the remaining water becomes increasingly difficult for plants to remove. Eventually, the soil reaches what's known as permanent wilting point. At that stage, water is technically still present, but it's held so tightly by the soil particles that roots can no longer extract it. So when we water trees, we're really trying to keep the soil somewhere between field capacity and permanent wilting point. Not soaking wet, not bone dry, just enough moisture to keep the tree functioning without removing the oxygen roots depend on.
So far, we've talked about what soil particles are made of and how they influence water movement. But here's something a lot of people don't realize. Two soils with the exact same texture can behave completely differently. That's because texture tells us what the soil is made of. Structure tells us how it's put together. Let's take a closer look.
So imagine this. You dump a pile of bricks into the middle of a room. Now imagine taking those exact same bricks and carefully building a house. The material didn't change, only the arrangement changed. Soil works the same way. Texture describes the size of the particles. Structure describes how those particles are arranged and held together. Healthy soils naturally form small clusters called aggregates. These aggregates develop because roots, fungi, bacteria, earthworms, insects, and decomposing organic matter all work together to bind individual particles into stable groups. Instead of acting like loose dust, healthy soils become a network of interconnected aggregates separated by pore spaces. Those pore spaces are incredibly important. Large pores, called macropores, allow rainfall to infiltrate, oxygen to circulate, and excess water to drain. Small pores, called micropores, store moisture for later use. When you have both working together, the soil behaves almost like a sponge. It absorbs rainfall efficiently, it stores moisture, it releases excess water, and it maintains oxygen around the roots. Organic matter plays a huge role in building this structure. As leaves, wood chips, roots, and other plant material decompose, they feed microorganisms. Those microorganisms produce sticky compounds that literally help glue those soil particles together. Mycorrhizal fungal also contribute to extending microscopic fungal threads throughout the soil, helping stabilize aggregates while increasing the tree's ability to access water and nutrients. This is why arborists often say we're not just caring for trees. We're caring for the soil ecosystem that supports them. Healthy structure doesn't happen by accident. It's built over years through biological activity. So unfortunately, soil structure, which is so important, can also be destroyed. One of the biggest causes is compaction, and we've talked about this a lot. Compaction occurs whenever enough pressure is applied to compress the soil. That pressure can come from many things: construction equipment, vehicles, repeated foot traffic, livestock, even years of mowing across the same areas. When soil becomes compacted, the particles are pushed closer together. and the pore spaces begin collapsing. So imagine squeezing a sponge in your hand. As you compress it, there are fewer places for water and air to exist. The same thing happens underground. Water infiltrates more slowly. Roots encounter greater resistance. Oxygen movement decreases. Beneficial microorganisms lose habitat. And because roots often grow where oxygen is available, compacted soils frequently produce shallow root systems. That is especially important in urban environments. Many trees planted in landscapes spend their entire lives fighting compacted soil. It's just kind of how it goes with urban landscapes. Think about your backyard. Sometimes homeowners notice symptoms like slow growth, early fall color, dieback, or thinning canopies and assume the tree just needs fertilizer or more water. In reality, the tree may simply be struggling because its roots don't have enough oxygen or enough physical space to expand. This is why arborists evaluate soil, not just the tree itself. Many problems that appear above ground actually begin years earlier below ground. Now let's bring everything together. Once rain reaches the ground, several different processes begin happening at the same time. The first is infiltration. Infiltration is simply the movement of water from the soil surface into the ground. Once water has entered the soil, gravity continues pulling it downward. The movement through the soil profile is called percolation. Along the way, some water drains completely out of the root zone. Some is stored within micropores. Some is absorbed by roots. Some eventually returns to the atmosphere through transpiration. Every one of those processes depend on soil texture, soil structure, organic matter, and compaction. Healthy soil doesn't just hold water. Healthy soil manages water. It accepts rainfall, stores what the tree needs, allows excess water to drain, maintains oxygen for respiration, supports billions of microorganisms, and provides an environment where roots can continue expanding year after year. As arborists, we spend a lot of time looking up into the canopies, but the truth is the story of every healthy tree begins underground. When we improve soil, we're not just improving dirt. We're improving the entire environment that makes tree life possible.
Okay, so we've been talking about soil compaction, so I wanted to do a little experiment. I have two of the same sized clear containers, and what I'm going to do is fill them with the same dirt, roughly the same amount. Except for one of these, I'm going to compact on purpose. So compaction happens from heavy rainfall, driving over gravel, soil, any construction, any kind of landscaping, settling over time, erosion. Compaction is extremely common. And this one I'm going to leave normal. And then what I'm going to do is pour about the same amount of water in each and show you the difference. Okay. So on the right, that's already draining. And on the left, there's still soil in there that's not even wet yet. So in a normal urban landscape, most of this water would be running downhill because it's very rare that we have flat, completely flat yards or landscaping, but you can see here the difference. Still on the left, that is still dry down below, and then the one on the right is fully saturated. And so what happens is the one on the right will drain much more quickly, and it will stay wet for less time. The one on the left will stay wet much longer if it has the opportunity to infiltrate at all. And so because it stays in there much longer, because it takes longer to infiltrate, it fills that pore space in the soil for longer and depletes that soil of oxygen. And so the tree needs to breathe and it needs to sweat, basically, just like humans. It breathes through the soil, through its roots, and it transpires through stomata, through its leaves. And so you can look straight down into there. You can see the one on the left is still pooled, the one on the right not at all. It's almost all the way drained. So that's just one example in real time of what soil compaction looks like and how structure of your soil affects a tree's ability to use and access water. Those are my trusted sidekicks. That's Pepper and that's Lily. Everybody, thanks for watching. Tune in next time. Thank you.
Soil may seem like one of the simplest parts of nature, but hopefully today you've seen just how incredibly complex it really is. The size of soil particles, the way they're arranged, and how water moves through them all work together to determine whether a tree has access to oxygen, water, and nutrients it needs to survive. The healthier the soil, the healthier the root system. And the healthier the root system, the healthier the tree. In part 3, we're going to explore something even more fascinating, the living side of soil. We'll take a look at bacteria, fungi, earthworms, insects, and the underground food web that makes healthy soil possible. If you're enjoying this series and want to continue learning the science behind trees, be sure to subscribe. Thanks for watching, and we'll see you in the next episode.